Good morning, everybody, the panel and the participant. Today, I will present my postgraduate research study on the topic trenching and encapsulation capacity of dendrimer with varying co-functionality and generation. This is my outline. I'm going through introduction, application, objective, and methodology. We have 5 steps in methodology and result, conclusion, and references. As an introduction to dendrimer, it can say that dendrimer, the word is made of two Greek words, dendro and meros. Dendron means tree and mero means part. Dendrimer are heavily branched structures that shapes like tree. They are well defined and has 3D structure. First found by Fritz Vogel in 1978. In a dendrimer, we can identify three major parts: core, generation, and coordination, and outer layer. And also we can identify internal cavity. Generation means how many homogeneous layers has occurred from core to outside of the layer, outside of the dendrimer. Coordination means how many number of branches attached to the core. And also you can see in the outer layer there are different type of functional group can be attached, and also you can see the internal core. This is an application of dendrimer. We can use dendrimer to deliver drugs to a specific location using targeted moiety that attach to dendrimer. We can attach drugs into dendrimer with as conjugated drug, encapsulated drug, and adsorbed drug. Our objective is in this study to find out the structural covalent relationship of a dendrimer, and no previous work has been carried on co-coordination. We use computational method because we can create a very pure system in silico, and also we can change the parameter as we decide. Also, we can observe uh, data that cannot be performed in real lab experiment. In methodology, we use molecular dynamics for to apply Newton laws to atoms, and we use software for visualization. We use visual molecular dynamics and to apply the real environment and the motion of atom. We use lamps, and we use cross-grain models, which mean between cross-grain model between and also we use cross-grain model for uh, design, which mean simplification of all atomic structure to several beads. For example, you can see there are protein that has a lot of atom, and it has simplified to several bead protein. And in step 1, we create in step 1 we create and in step 1 we create our dendrimer. We create our dendrimer as outer layer is hydrophilic and internal core is as hydrophobic. So for that, we use MH, CH, and BH. This MH and CH are coding purposes and naming purpose. So in MH bead in middle core, it is CH2, CH2, and it grows to another CH2, CH2, and with the BH bead, it begin to branching, and also it also continue to another ester group. Uh, like after the growing to several generation, finally it meet outer layer. It is hydrophilic, and we use ether and hydroxyl group to make dendrimer outer layer is hydrophilic. In step 2, we create different dendrimer with different co-coordination. You can see here C1 is one branch begin from core, and C2 mean uh, two branch begin from the core. As likewise, uh, we create C1, C2, and C3 until C6, and also we create a different generation. Uh, that mean G3 to G5. G3 mean there are three homogeneous layers from core to outer layer of when goes to core to outer layer, and also we get um, three different dendrimer G3, G4, and G5. So far we have created different coordination and different generation of dendrimer, and the next step was to equilibrate those dendrimer in water phenol and water phenol system, and we use different type of mathematical and computational ways to determine the behavior of the dendrite. Use this condition in our simulation: temperature 300 Kelvin, pressure 1 atm, and we use no-scope algorithm to keep the T and P constant, and to apply a real uh, realistic condition. And also we use RESPA integrator method to determine our trajectory. In step 3, we equilibrate dendrimer in water. So here what we did is we took the dendrimer and kept inside a water box and let it equilibrate. we observe we observe our simulation under 20 nanosecond for 1000 frame. That means one frame represent 1 nanosecond represent 50 frame represent 1 nanosecond. You can observe the dendrimer is changing its shape over the time. Also, we equilibrate dendrimer in phenol. We kept dendrimer inside a phenol box and let it equilibrate. And also, we observe the same pattern, like it change the shape over the time. And most importantly, this is our system to determine how much drug can be captured inside the dendrimer molecule. What we did here is we took uh, phenol as our basic drug. That means phenol. We choose phenol because phenol has fast diffusion rate and intermediate hydrophobicity, similar to the many small drug. And the the equilibrate dendrimer with the drug molecule kept inside the water box, and this water box was saturated by uh, bottom phenol layer. We use this bottom phenol layer to saturated these um, water box. Otherwise, it's try to make phenol droplets inside the water box. So we kept temperature 300 and pressure atm and let it equilibrate. This is our simulation. This is our observation. We observe the initial captured drug molecule, which is in red, is come out came outside of the dendrimer, and also dendrimer try to capture the drugs molecule outside in the water solution, water layer. We use different parameters methods to determine the structure and behavior of the dendrimer. We use radius of gyration value, which mean how much the mass is spread from core to outside of the dendrimer, and also we use white volume fraction to determine how much void space is containing inside the uh, dendrimer. And this is our radius of gyration values. We plot radius of gyration values versus different co-coordination, and also we plot radius of gyration value versus generation. We observe radius of gyration is increasing when we change the when we increase the co-coordination, simply because when we increase the co-coordination, dendrimer mass is trying to condense over surf near surface. And also when increase the generation, it is obvious that the mass is increasing, the number of homogeneous layers are increasing. And the void volume, we try to observe the void volume fraction. The fraction is equal to the volume fraction of a component is equal to a probability of the component divided by the total number of probe points. Here we plot the volume fraction versus distance from core bead for different component of the solution, like dendrimer, solvent, drug, and the volume void volume. You can see here the void volume is very negligible. And we try to observe the hydrophobic and hydrophilic bead distributions of the dendrimer in different solution. And also we try to get the data of loading capacity and fit those into an equation. This is our dendrimer behavior in water. Here we plot the normalized probability of hydrophilic and hydrophobic beads for different generation and different co-coordination. This so you can observe here in dash line they are hydrophilic, and solid line it is hydrophobic. It is hydrophobic. So hydrophobic beads are more distant from core to more stay away from core beads, and while hydrophobic beads are stay close to the core. And also we try to observe the behavior in phenol. We plot the normalized probability versus distance from core bead, and we observe the same pattern like in water, like hydrophilic beads are more distant from core, and while hydrophobic beads are stay close to the core. Hydrophilic and hydrophobic bead distribution of in we and also we try to observe hydrophilic and hydrophobic bead distribution of in different system. Same like before, we plot the normalized probability versus distance from core bead. Distance from core bead. What we observe here is in water the dendrimer is most stretched, and as phenol is more polar than water, the dendrimer try to stretch than in water. Uh, and also the most stretch is in because in our water phenol system, because the water layer is trying to stretch the dendrimer outer surface, and the captured drug molecule, try to expand the dendrimer inner core. This is our loading capacity of dendrimer data, and we try to get the loading capacity of a dendrimer. Loading capacity means how much drug molecule can be captured with respect to its mass as a percentage. And we try to fit those data into this equation. MR mean loading capacity, MI mean initial excess loaded capacity, ME mean interrupted mass at time t. P is a decaying constant, and T dash is and T is time parameters. This is how we plot the loading capacity and different co-functionality. We plot loading capacity versus time for different co-coordination, and we observe infrared it has highest loading capacity for the dendrimer. This is our predicted parameters. This is our predicted graph for 100 nanosecond, and you can observe that in red C5 dendrimer has the highest stability, and we plot and we try to fit those data into this equation, and we observe 56% for G5 dendrimer, and those data was fit around 0.98 R squared value. And also we try to fit those data into loading capacity of different generation. We plot loading capacity versus time for different generation, and we observe the G5 has the highest stability, and we fit those data into different generation, and we fit those data into this equation, and we observe 87% for G5, and those data fitted around 0.98 R squared value. This is our predicted graph for different generation. And as a conclusion, I can say that when we change the co-coordination while keep the generation is constant, C5 has the highest ability to capture the drug molecule, and C1 doesn't have any ability to capture any drug, and C2 has the lowest, while C3, C4 and C6 are in between C2 and C5. Also when we change the generation while keep co-coordination constant, G5 has the highest ability to capture the drug molecule, and G3 is the lowest, and G4 was in between them.